So we've learned about the cost function landscape, and we've learned that we found out that we're trying to find this algorithm that's going to take us from some of the highest peaks of that cost function landscape where the error is really high, all the way down to the bottom where the cost function and the error is the lowest. And that algorithm is going to be gradient descent. So gradient descent is going to find the configuration of the model parameters that lead to the lowest error. And it's going to do it iteratively, step by step. And so for our function, which is, convex, it's a nice bowl shape, it's actually very easy to find the lowest error, the minimum point on that landscape. But for some functions that are not convex, they can have many hills, because let's just say there's some functions where there's some models that have millions of parameters or many parameters, and the cost function landscape is really hilly, and so there's many valleys. Some valleys are steeper than others. We just have one valley in ours. And so in that case, gradient descent is not always going to find the lowest possible error across all the cost function landscape. It may find what we call local optima, which is just one valley in that landscape. It doesn't mean it can't find the global optima, which would be the biggest valley in that landscape. It just means that it won't always do that. And so you may have to run gradient descent from several different points on that landscape until you find one that gives you the best value. But you'll never really know where is the global optima for more complicated cost functions and models with lots of parameters. So how does gradient descent work? And so without delving too much into the math here, if you know what a derivative is, essentially with gradient descent, what we're going to do is we're going to calculate the derivative of our cost function with respect to each one of our parameters. So in our case, we have just two parameters. We have m and b, and we're calculating the derivative of our cost function, which is the mean squared error, with respect to m and also with respect to b. Now that we have the derivative, which is going to give us the steepness of the slope in that direction on our cost function landscape, and then also it's going to give us the steepness of the slope with respect to both of those in the direction of both of those parameters. So it's going to give us the steepness of the slope with respect to this particular parameter, and that comes with it a direction. So this derivative says that in the direction of m on this cost function landscape, this is how steep the slope is. And same thing for b. And then, since we have the steepness of the slope, we have the direction of that slope, we just need to figure out how much of a step we want to take in that direction. So we're going to modify that slope a little bit, because maybe we don't want to take too big of a step. And so what we factor in now is this concept of a learning rate, which you'll commonly see referred to as step size. I think learning rate and step size are both intuitive. But a step size could be more intuitive in this case. But essentially, the derivative is going to give you the steepness of the slope and in what direction you need to move to get to the bottom of the hill. And then the learning rate is going to tell you how big of a step you need to take in that direction. And so we're going to subtract the learning rate times the derivative from each parameter. Now, I said that the derivative is going to give you the direction in terms of like how to get to the bottom of the hill. It doesn't naturally do that. A true partial derivative is just going to give you the steepness of the slope, but the arrow of the direction is going to point up towards the top of the hill and in the direction of steepest ascent. That's not where we want to go. We want to go down to the bottom, and so we need to multiply it by -1, which is essentially what this minus sign does, and that flips the arrow from steepest ascent to descent. So now we have the direction pointing towards the bottom of the hill. And so let's get a visual understanding of that. That's going to help us drive home this lesson. So here I have functions to calculate the partial derivatives with respect to m and b, and then I have this function that's going to plot it's going to plot our cost function landscape, and the hover label is going to give us our derivative. I'm going to start at m equals -7 and b equals 30. We know that to be not a good solution, and what we're going to see is we're going to start up here, And so with m, if our equation is y equals negative 7x plus 30, then our cost function is going to be 3780. That's a really high cost. That's not what we want. We want to be, again, remember, we're trying to get down here. We're trying to take this ball, roll it down the hill to get to some of these lower points, or in our case, the lowest point. But here we go. This is where we're starting at, and gradient descent is going to take us to the bottom. And so the derivative with respect to m here is negative 6.16. And the derivative with respect to b here is 0.6. Now, I will say that I am showing these derivatives after I've already applied the learning rate. So the derivative is actually bigger than negative 6.16 for m. What I'm doing is multiplying it by 0.01. And so sometimes the learning rate not only the learning rate lets you control how big of a step you want to take in the direction of m or b in our case, because sometimes the gradient can be really big, and if you don't apply a learning rate to sort of shrink that number, you could wind up not taking a step in this direction like to here. You could wind up overshooting and taking a step like that's really big, and you wind up over here with a really high cost, and then taking a big step that winds you up over here, and then over here, and then over here, and you'll never optimize because you're taking too big of steps. And so if you take too big of a step, like if your learning rate is not small enough, or if your learning rate is not small enough, let's just say it's 1 or even more than 1, you'll never optimize. You'll just bounce around because you're taking too big of steps. You're like literally jumping across the landscape here. If learning rate is too small, you're taking too small of steps, it could take literally forever for you to reach the bottom. And so you want to find a balance. I wanted to talk about that really quickly about the learning rate. So this is the modified gradient already by the learning rate. It's telling me I need to subtract negative 6.16 from m, because that's how we update, and then subtract 0.6 from b to move this ball in the direction that is closer to the bottom of the hill. And so let's do that. I'm going to subtract off, I'm going to manually update these parameters. Negative 6.16, I'm only going to do the first 2 decimal places. Negative 6.16, and then for b, what was it again? 0.6. So I'm going to subtract off 0.6. Now remember, the cost is 3780. This update should move that ball down that hill and actually get us to a point where we have a lower cost. And it's already looking good. Our cost now is $12.35. That's a lot better. Now we're going to update it again. We're going to subtract negative 1.97 away from m. Negative 1.97. And we're going to subtract 0.58 from b. Let's see where we get. And 944, that's better than 1235. Let's do one more update to see if the cost keeps going down, which it will, but it's always good for the sake of demonstration. We're going to subtract off negative 0.63 from m, and let's subtract off 0.57 from b. Let's see where that gets us. Yeah, 884. So we're getting better. And as you see, the derivatives are getting smaller, and that's how it should be, because remember, the derivative not only gives us a direction of steepest ascent, but we're flipping it, this direction of steepest descent, but it gives you the steepness of the slope. And so up here, of course, the slope is steeper. I mean, if you were standing on this, I mean, and this was slippery, you would just slide down really fast. Yeah, so that's actually a really good analogy. Imagine you're sitting on this thing and you're sliding down it. You would be sliding down really fast here because the slope is super steep. But as you got to the bottom, you would sort of slow down because the steepness of the slope would become less and less and less, and flatter and flatter and flatter. And so you would actually be moving slower. And so gradient descent is actually going to make big strides. If you're up here, gradient descent is going to take you all the way down here. And then what's going to happen from here is you're going to make smaller and smaller strides until eventually you get down here into like the really like low points where you're barely making any progress with each iteration. And so we don't want to do that manually because it would take forever. And so let's write some code to start from -7 and 30 and then automatically update the parameters. And let's see what that looks like over many, many iterations. In our case, we did 203. And as you can see, we start here at 3780. Our first iteration takes us all the way down to 1234. Our second one takes us to 943. And then our third one to 883. And then 50 iterations later, we're at 201. 50 after that, we drop another 100 down to like 97. And then 50 after that, we drop to 83. And now from the next 50, we go from 83 to like 81 and some change. And so you see, like in these later iterations, it's making very small progress, albeit progress, until eventually it's going to not make any more progress. It's going to find the lowest point. And so that's gradient descent. It's rolling that ball down the hill, and then if we plot the point that it found at the end of all of its iterations, we can see that it's at the lowest point, or it's got to be near the lowest point. And here it is. The slope, it found that the best slope is m equal to 2.06. The best intercept is 0.44, and that's going to give us a cost of 81.72. And at this point, the slope of the gradient in the direction of m, or the derivative with respect to m, is 0. Or at least that's a rounding. It's rounding up to 0. And so it's not optimizing m anymore. What it's doing is it's optimizing b. And so b still has a tiny bit of slope, and a tiny bit more can go. And so it's edging b in the direction of steepest descent, and it's optimizing it for the lowest error. And so that's how gradient descent works. We're iteratively updating those parameters one step at a time over several iterations to be able to produce the set of parameters that optimize our cost function. And as you can see, if we had many parameters, this would take a really long time to do. And so thankfully we have computers to do it for us. And that's gradient descent.